Philadelphia, 1873. The Pennsylvania Railroad's chief engineer examines the wooden model on his desk with barely concealed contempt. 3 vertical cylinders, gears connecting to every wheel, a boiler that sits off-center, and he slides it back across the mahogany with one finger. This is a logging toy, not a locomotive. But in the mountains of Michigan, that toy was already hauling loads that would snap the drawbars of his prize freight engines. The tyranny of the gradient. For 50 years, every railroad engineer in America knew the same immutable law. A standard locomotive could not climb a grade steeper than 3 to 4%. Period. This was not opinion. This was physics. The mathematics were brutal and unforgiving. Adhesion, the friction between a steel wheel and a steel rail, could only generate so much tractive force before the wheels spun uselessly. The heavier you made the locomotive to increase that adhesion, the more power you needed to move its own weight. The equation ate itself. At 4% grade, a locomotive climbing 100 feet would travel 2,500 feet horizontally. That is a gentle rise that feels almost flat when you walk it. But to a steam locomotive, it was a wall. Engineers could push to 5 or 6% for short distances if they were willing to risk wheel slip, broken couplings, and the constant terror of a runaway train on the descent. Anything steeper was considered suicide. This limitation was not just an engineering annoyance. It was an economic straitjacket that confined American industry to the flat lands. The Appalachian Mountains held billions of board feet of timber. The Rockies contained veins of copper and silver so rich that prospectors could see the ore glinting in the exposed rock. The Sierra Nevada forest grew trees so massive that a single trunk could yield enough lumber to build an entire house. All of it was worthless. Not because it did not exist, but because it could not be moved. The standard solution was to cheat the terrain. Railroads carved switchbacks into mountainsides, zigzagging back and forth to reduce the effective grade. This worked, but it turned a 5-mile journey into a 20-mile ordeal. The construction costs were staggering. Every additional mile of track meant more grading, more ties, more steel, and more labor. And at the end of all that expense, you still had a line that could barely function. Trains had to be broken into smaller consists. Locomotives had to double head, with 2 engines straining to pull half the normal load. The alternative was even worse. In some logging operations, they simply gave up on rails entirely. They built elaborate systems of wooden flumes, essentially artificial rivers, that carried logs down mountainsides on rushing water. Others used cable inclines, where stationary steam engines at the summit winched cars up and down on steel ropes. These systems worked, but they were slow, dangerous, and expensive. And they could only move logs in one direction, downhill. Railroad engineers accepted this as the natural order of things. They designed locomotives to be bigger, heavier, and more powerful, always trying to squeeze a bit more adhesion out of the same basic architecture. But they were optimizing within a paradigm that had already reached its theoretical limits. The conventional wisdom, the standard American locomotive of the 1870s, was a masterpiece of mechanical engineering, refined over decades of incremental improvement. Horizontal cylinders mounted near the front, driving rods connected to large-diameter driving wheels, and a rigid wheelbase that distributed weight across a handful of axles. This architecture had conquered the prairies, crossed the continent, and built an empire. It was the template that every serious railroad followed. The design philosophy was elegant. Power came from cylinder size, and steam pressure. Speed came from large driving wheels that covered more ground per revolution. Efficiency came from mechanical simplicity and standardized parts. A good freight locomotive might have 4 or 5 sets of driving wheels, each 6 feet in diameter, all connected by side rods that forced them to turn in perfect synchronization. This rigid connection was considered essential. If one wheel slipped, the others would keep pulling, or so the theory went. But this conventional wisdom contained a fatal assumption. It assumed the track would always be relatively level, and the load would always be behind the locomotive. The entire machine was optimized for horizontal pulling force on gentle grades. The large driving wheels were magnificent for speed on flat track, but they were a disaster on steep grades. The taller the wheel, the less torque it could generate. A 6-foot diameter driving wheel needed enormous force from the cylinders just to overcome its own rotational inertia. The rigid connection between driving wheels created another problem engineers had learned to accept as unavoidable. On curves, the inside wheels had to travel a shorter distance than the outside wheels. But because they were rigidly connected, they could not turn at different speeds. The result was wheel slip, binding, and accelerated wear. Railroads simply built gentler curves and replaced rails more often. It was expensive, but it was the cost of doing business with the only locomotive design that worked. The engineering establishment understood the physics perfectly. Adhesion was a function of weight multiplied by the coefficient of friction between steel wheel and steel rail. That coefficient was fixed by the laws of physics at roughly 0.25. A 60-ton locomotive could theoretically pull 15 tons up a grade before its wheels slipped. But this assumed perfect conditions. In reality, you were lucky to achieve half that performance. The accepted solution was to add more weight to the driving wheels. This led to increasingly massive locomotives with longer wheelbases and more driving axles. But size created its own problems. Longer wheelbases could not navigate sharp curves. Heavier locomotives required stronger bridges and more robust track. Fundamentally, you were just making an inefficient system bigger. The paradigm remained unchanged. Railroad mechanical departments published papers explaining why gears were impractical for serious railroading. Gears added complexity and maintenance. They reduced speed, making them useless for mainline service. Most damning of all, they violated the basic principle of locomotive design: direct connection between pistons and wheels. Gears were for stationary machinery and mining equipment, not for serious transportation. This consensus was so strong that when loggers in the North Woods began experimenting with alternative designs, the railroad establishment dismissed them as backwoods tinkering. These men were not real engineers. They had not studied thermodynamics at technical colleges. The fact that their solutions might actually work better than conventional locomotives was literally unthinkable to men who had spent their careers perfecting the standard design. The logger who saw different. Ephraim Shea was not a railroad engineer. He was a logger, a sawmill operator, and a man who watched his profits disappear into the gap between forest and market. By 1870, he was running a lumber operation near Herring, Michigan, deep in the northern forests where the best timber grew on slopes that would make a railroad engineer weep. His logs were first-rate. His lumber was in high demand. But getting the raw timber from stump to sawmill was slowly bankrupting him. Shea understood the problem intimately because he lived it every day. His crews would fell massive white pines, trim them, and prepare them for transport. Then came the nightmare. Teams of horses would drag the logs to a central skidway, a brutal process that damaged the timber and exhausted the animals. From there, the logs had to be loaded onto wagons for the trip to the mill. In dry weather, the wagons sank into soft ground. In wet weather, they became completely immobile. A single large log might require 8 horses and most of a day to move 3 miles. The economics were devastating. Shea calculated that transportation costs were eating nearly 40% of his revenue. He was paying his logging crews to cut timber, then paying teamsters to move it at a pace that would have embarrassed a medieval merchant. Meanwhile, his competitors who owned timberland on flat ground near existing rail lines could harvest and ship for a fraction of his cost. The resources were identical. The market price was identical. But the terrain made Shea's operation uncompetitive. He considered building a conventional railroad spur up to his timber stands. The surveyors delivered their estimate, and Shea understood immediately that it was impossible. To keep grades under 4%, the line would need extensive switchbacks, adding miles of track to cover a straight line distance of less than 2 miles. The construction cost exceeded the value of all the timber on his land. He could build the railroad or harvest the forest, but he could not do both profitably. This was the trap that conventional railroading created. The technology was so constrained by its own limitations that entire regions were economically isolated. Shea could see the problem clearly because he stood at the exact point where railroad efficiency collapsed. He did not need a locomotive that could pull a 100-car freight train at 30 miles per hour across Nebraska. He needed a locomotive that could pull 20 tons of logs up a 12% grade on cheaply built temporary track. Speed was irrelevant. Elegance was irrelevant. The only metric that mattered was tons hauled per dollar spent. Shea began experimenting in his own machine shop during the winter of 1870 to 1871, when logging operations shut down and his equipment sat idle. He was not trying to invent a revolutionary locomotive. He was trying to solve his own immediate problem with the tools and materials he had available. His background was in sawmill machinery, where gears and belts transferred power at different speeds and torques. He understood that you could trade speed for power through mechanical advantage. The breakthrough came from rejecting the assumption that had trapped every railroad engineer. Shea did not care if his locomotive could not go fast. He did not care if it looked ugly or violated engineering aesthetics. He cared about one thing: could it turn every revolution of the pistons into maximum pulling force on steep grades? The answer required abandoning direct drive entirely and embracing what the establishment considered a weakness: gears. Shea mounted his cylinders vertically on the right side of the boiler. The vertical orientation meant the pistons drove a horizontal crankshaft that ran the entire length of the locomotive. That crankshaft connected through bevel gears to a drive shaft that ran alongside the frame. That drive shaft, in turn, connected through more gears to every single wheel on the locomotive and tender. The result was a machine where every wheel was a driving wheel, powered independently through its own gear set. The machine that emerged from Shea's shop in 1871 looked like nothing the railroad world had ever seen. Where conventional locomotives were symmetrical and balanced, Shea's design was visibly lopsided. The boiler sat offset to the left. The vertical cylinders and their associated valve gear jutted out on the right side like a mechanical growth. The wheels were absurdly small, barely 3 feet in diameter, making the locomotive appear squatted and ungainly. Railroad men who saw photographs of it later would use words like crude, primitive, and amateur. They were all missing the point. Ugly did not mean useless. The genius was in what happened beneath that exterior. The vertical cylinders drove a crankshaft that looked more like something from a factory than a locomotive. Instead of the reciprocating motion of conventional side rods, Shea's crankshaft rotated continuously. This rotation was transmitted through a bevel gear at 90 degrees to a longitudinal drive shaft that ran along the right side of the entire locomotive frame. This drive shaft was the heart of the system. It carried power from the cylinders to every wheel on the machine. Each axle on the locomotive connected to the drive shaft through its own set of bevel gears. This meant that every wheel received power independently. If one wheel encountered an obstruction or a patch of low friction, it would slip while the others continued to grip and pull. The locomotive did not rely on any single point of adhesion. It distributed pulling force across every wheel, and because those wheels were small and numerous, the total adhesive weight was far greater than a conventional locomotive of the same size. Every wheel mattered. The mathematics of this design demolished the assumptions that had governed railroad engineering for decades. A conventional locomotive might have 4 sets of driving wheels, with a total adhesive weight of 40 tons. Shea's locomotive, even though it weighed less overall, had 6 sets of driving wheels plus the wheels on the tender. All powered, every pound of the locomotive's weight contributed to adhesion. Nothing was wasted on unpowered leading or trailing trucks. The gearing ratio was the secret weapon. Shea could select different gear ratios depending on the grade. For extremely steep terrain, He geared the locomotive way down, sacrificing speed for torque. The pistons might make 100 strokes per minute, while the wheels turned just 15 times. This gave the locomotive enormous pulling power at walking speed. To a railroad engineer accustomed to 40 miles per hour freight trains, this seemed pathetically slow. To a logger who had been moving timber with horses, it was a miracle. Torque won, where speed did not. The small wheel diameter created another advantage that was not immediately obvious. Large diameter driving wheels on conventional locomotives needed perfect track alignment. Shay's small wheels could roll over obstacles that would stop a conventional engine. Small wheels, combined with gearing and distributed drive, let the locomotive go where others could not. The flexible geared drive meant that wheels could move up and down independently without binding the machinery. The locomotive could operate on track that was barely more than wooden rails spiked to logs laid in the dirt. This was the revelation that the establishment could not accept. Their entire engineering philosophy was built on the assumption that locomotives required precisely graded roadbeds, carefully laid track, and gentle curves. Shay's design proved that, with the right mechanical arrangement, a locomotive could operate on infrastructure that would horrify a civil engineer. The track could climb at grades up to 15%. It could twist through curves so sharp that conventional equipment would bind and derail. Word began spreading through the logging camps of northern Michigan. There was a machine that could go where horses could not, that could pull loads no conventional locomotive could move, and that could operate on temporary track built at a fraction of normal railroad construction costs. The demonstration. The first commercial demonstration of Shay's locomotive came in 1873, when a lumber company in Pennsylvania agreed to test the machine against their existing logging operations. The company operated in mountainous terrain where conventional railroading was impossible. They had invested heavily in cable inclines and horse teams, accepting the high costs as unavoidable. Shay arrived with his locomotive on a flat car, assembled it at the site, and offered to prove his claims. The test course was deliberately brutal. A grade averaging 10%, with sections hitting 12%. Track laid on rough ties with minimal grading. Curves that would have derailed conventional equipment. The lumber company's superintendent was skeptical, but he was also desperate enough to give anything a chance. If this contraption could move timber where nothing else could, it would transform their entire operation. Shay coupled his locomotive to a string of log cars loaded with 20 tons of rough-cut timber. The load was not particularly heavy by railroad standards, but the grade made it effectively impossible for conventional equipment. He opened the throttle, and the little locomotive began to climb. The vertical cylinders churned, the crankshaft rotated, and power flowed through the gears to all 12 wheels. The locomotive gripped the rails and pulled. It climbed steadily, maintaining a walking pace but never faltering. The wheels did not slip. The machinery did not bind. When the locomotive reached the steepest section, where the grade hit 12%, observers held their breath. A conventional locomotive would have stalled here, wheels spinning uselessly. Shay's machine kept pulling. The geared drive distributed power so effectively that even when individual wheels encountered low friction spots, the others compensated. The locomotive topped the grade and delivered its load to the sawmill. The return trip was equally impressive. Descending steep grades had always been the terror of railroad operations. Brakemen rode on every car, manually setting brakes to control speed. Runaways killed logging crews regularly. Shay's locomotive descended under perfect control. The geared drive worked in reverse, allowing the engine itself to provide braking force. The small wheels and low speeds meant that even if control was lost, the resulting accident would be survivable rather than catastrophic. The Pennsylvania Lumber Company calculated the economics immediately. One Shay locomotive could replace 6 teams of horses and their teamsters. It could operate 16 hours a day, compared to the 8 hours that animal power could sustain. Most importantly, it made timber accessible that had been previously unharvested. A stand of trees 2 miles from the mill had been written off as too expensive to log. With Shay's locomotive, that timber became profitable. The company ordered 2 more locomotives before the test was finished. Other logging operations heard about the Pennsylvania success and demanded demonstrations. Shay's small shop in Michigan could not keep up with orders. Each locomotive was essentially custom-built, adapted to the specific terrain and requirements of the buyer. But the core design remained consistent: vertical cylinders, geared drive, small wheels, maximum adhesion. The ugly machine that violated every railroad engineering principle was suddenly the most sought-after locomotive in the timber industry. The numbers told a story that railroad engineers could not ignore, even if they wanted to. A conventional 50-ton locomotive operating on a 4% grade could pull its own weight, about 50 tons, under ideal conditions. Shay's 30-ton locomotive, operating on a 12% grade, could pull 60 tons. The power-to-weight ratio was so superior that it seemed to violate physics. It did not, of course. It just exploited physics in ways that conventional thinking had never considered. The first time a Shay locomotive appeared at a major railroad equipment exposition, the reaction was immediate and brutal. The year was 1875. The location was Philadelphia, and the audience was every important railroad mechanical engineer in the eastern United States. They walked past gleaming conventional locomotives, admired the latest improvements in valve gear and boiler design, and then they saw Shay's machine. The laughter started as a murmur and built to open derision. Someone coined the term toy locomotive, and it stuck. The vertical cylinders looked like a factory engine grafted onto a railroad frame. The exposed gearing seemed crude and vulnerable. The small wheels were absurd. Most damning of all, the entire machine was asymmetrical, violating the aesthetic sensibility that railroad men had developed over decades. Locomotives were supposed to be balanced, powerful, and fast. This thing was none of those things. The engineering journals published reviews that ranged from dismissive to hostile. One prominent mechanical engineer wrote that geared locomotives represented a fundamental misunderstanding of railroad economics. Another calculated that the complexity of the gearing would result in constant breakdowns and maintenance costs that would erase any advantage on steep grades. A third simply stated that no serious railroad would ever purchase such equipment. The establishment's rejection was rooted in institutional blindness. Railroad engineers thought in terms of mainline service, long distances, heavy trains, and maximum efficiency at speed. Shay's locomotive was designed for the opposite application. It was solving a problem that the railroad establishment that did not even recognize as real. Logging railroads were temporary industrial expedients, unworthy of real engineering attention. The Pennsylvania Railroad's chief mechanical officer was shown Shay's design and asked for his opinion. His response was withering. He calculated that the geared drive absorbed so much power in friction losses that the locomotive was grossly inefficient compared to conventional direct drive. He concluded that while the machine might have some limited utility in logging operations, it represented a dead end in locomotive development. Serious railroads would continue to use serious locomotives. This attitude was not just professional pride, it was economic self-interest masquerading as engineering judgment. The major railroads had invested millions in infrastructure designed around the limitations of conventional locomotives. If Shay's design proved that steep grades were actually practical, all of that investment became questionable. The locomotive manufacturers shared this institutional resistance. Companies like Baldwin, Brooks, and Rogers had perfected the conventional locomotive design. Geared locomotives represented a completely different manufacturing paradigm. To embrace Shay's design would mean admitting that their entire product line was solving the wrong problem. But while the establishment mocked, the market was speaking. Lumber companies did not care about engineering aesthetics or institutional pride. They cared about moving timber profitably. The toy locomotive was becoming an industry. The avalanche. By 1878, the contempt of the railroad establishment had become irrelevant. The market had rendered its verdict, and that verdict was overwhelming. Shay could not build locomotives fast enough. He partnered with Lima Machine Works in Lima, Ohio, a company that had the manufacturing capacity to scale production. Lima would build over 2,700 Shay locomotives over the next 60 years. But they were just the beginning. The Climax Manufacturing Company emerged in 1888 with a competing design. Instead of vertical cylinders on one side, the Climax used two cylinders mounted at an angle, driving a two-speed transmission that powered all wheels through a central jackshaft. The mechanical arrangement was different, but the principle was identical. Geared drive, maximum adhesion, steep grade capability. The Climax eventually produced over 1,000 units. Heisler Locomotive Works introduced yet another variation in 1891. Their design placed a V-twin engine in the center of the locomotive, driving gears on both sides of the frame. This created a more balanced machine that addressed one of the few legitimate criticisms of the Shay design. Over 600 Heisler locomotives were built. The explosion of geared locomotive manufacturing represented more than just market demand. It represented a fundamental shift in how engineers thought about railroad problems. Geared locomotives proved that a completely different paradigm was not only possible, but economically superior for a huge range of applications. Mining operations in mountainous terrain adopted geared locomotives as fast as they could acquire them. A copper mine in Colorado ordered 3 Shay locomotives to haul ore from mountain claims down to a valley smelter. The grades were so steep that conventional haulage would have required an elaborate cable system. The Shays handled it with routine mechanical operation, running 16-hour shifts and paying for themselves within a year. The logging industry underwent complete mechanization. Before geared locomotives, large-scale logging was only economical in relatively flat terrain with river access. Shay, Climax, and Heisler locomotives opened vast timber stands that had been inaccessible. The great forests of the Pacific Northwest, previously too remote and too mountainous for profitable logging, suddenly became the center of American timber production. An entire industry transformed in less than a decade. Even the railroad establishment began, reluctantly, to recognize reality. Branch lines in mountainous terrain that had been considered impossibly expensive to build with conventional standards became feasible with geared locomotives. A geared locomotive operation could be built in 6 months with a fraction of the investment. The toy locomotive was becoming indispensable. By the turn of the century, the most advanced Shay locomotives could pull over 100 tons, up a 15% grade. This was performance that simply had no equivalent in conventional railroading. The American innovation, born from one logger's frustration with terrain, became a global solution to a problem that existed wherever mountains met economic necessity. The economic earthquake. The availability of practical steep-grade locomotion created economic effects that rippled far beyond the railroad industry itself. Entire resource industries that had been constrained by transportation costs suddenly became viable. The transformation was not gradual, it was explosive, restructuring regional economies across North America within a single generation. The timber industry provides the clearest example. In 1870, American lumber production was concentrated in the accessible forests of the upper Midwest and the flat coastal regions. The vast mountain forests of the West were known to exist, but the economics of harvest and transportation made them worthless. A logger could cut a massive Douglas fir in Oregon, but the cost of getting that log to a sawmill exceeded its market value. Geared locomotives shattered that bottleneck. By 1900, the Pacific Northwest had become the center of American timber production. Towns like Tacoma, Portland, and Seattle transformed from modest coastal settlements into booming industrial centers. The lumber arriving at their docks came from forests that had been economically inaccessible 30 years earlier. Mining experienced a parallel transformation. The richest ore bodies in North America were frequently located in terrain so rugged that conventional transportation was either impossible or prohibitively expensive. Geared locomotives converted previously marginal operations into highly profitable enterprises. The cost comparison was stark and undeniable. A conventional railroad reaching a mountain mine might require 5 miles of track, extensive grading, and multiple switchbacks to achieve a 2-mile straight-line distance. Construction costs could easily reach $50,000 per mile. A geared locomotive operation could often build a direct route with minimal grading. The same 2-mile connection might cost $15,000 total. The cumulative effect was a redistribution of population and economic activity across the American landscape. Before geared locomotives, mountains were barriers that confined development to accessible lowlands and river valleys. After geared locomotives, mountains became penetrable. Towns appeared in locations that would have been impossible a generation earlier. Industries exploited resources that had been visible but untouchable. The geography of possibility expanded. The golden age of geared logging locomotives lasted roughly 60 years. By the 1930s, the combination of diesel trucks, improved roads, and the depletion of easily accessible timber began to erode their economic advantage. Logging operations that had once required railroads could now use trucks on forest roads. The flexibility and lower capital cost of road transportation eventually proved superior for most applications. The last Shay locomotive was built in 1945. Lima Locomotive Works, which had manufactured thousands of geared locomotives, shifted entirely to other products, but the technological principle that Shay discovered did not disappear. It evolved and adapted to new applications. Modern rack railways use geared drive systems to climb grades that would be impossible with adhesion alone. The Pilatus Railway in Switzerland climbs grades exceeding 48% using a rack and pinion system that is a direct descendant of Shay's innovation. Tourist railroads in mountainous regions still operate preserved Shay and Climax locomotives, demonstrating to modern audiences the capabilities that seemed impossible to 19th-century railroad engineers. The broader lesson of the geared locomotive story extends far beyond railroad technology. It is a lesson about paradigms and the danger of optimizing within incorrect assumptions. The railroad establishment had spent 50 years perfecting the conventional locomotive design. They had created machines that were elegant, efficient, and powerful within their operational envelope. But that envelope was narrowly defined, and they had become psychologically incapable of questioning its boundaries. Shay was able to solve the steep grade problem precisely because he was not a railroad engineer. He was not invested in the conventional paradigm. He did not care about the aesthetic principles that governed locomotive design. He did not worry about violating the accepted wisdom about direct drive and large diameter wheels. He looked at the problem with fresh eyes and asked a question that railroad engineers had stopped asking. What if we did this completely differently? This pattern repeats throughout industrial history. Breakthrough innovations rarely come from the establishment. They come from outsiders, who do not know what is supposed to be impossible. The railroad barons who mocked Shay's toy locomotive were not stupid or incompetent. They were brilliant engineers who had optimized themselves into irrelevance. They had become so good at solving the wrong problem that they could not recognize the right problem when it rolled into their exhibition hall on small wheels with gears hanging out the side. The modern equivalent is visible in every industry where established players struggle to respond to disruptive innovations. The incumbent has infrastructure, expertise, and institutional knowledge, all optimized for the existing paradigm. The disruptor has none of that baggage. They can build something that looks wrong, performs poorly by conventional metrics, and yet solves the actual problem better than the elegant solution ever could. The toy locomotive becomes the industry standard while the establishment is still explaining why it cannot possibly work. Today, when engineers confront impossible problems, they should remember Ephraim Shay and his ugly, asymmetric, slow locomotive that did what the experts said could not be done. Sometimes the solution is not building a better version of what already exists. Sometimes the solution is building something completely different that violates every rule you have learned. The railroad barons laughed. Then, they bought Shay locomotives. That is the pattern. The market does not care about aesthetics or conventional wisdom. It cares about results, and results have a way of silencing mockery.